We published one paper last year in December, one just arrived today, and we are about to write like one or two in next week, I hope. So I choose a very lyrical title, of course, which is a reference to Tolkien, Bag End. I mean, I'm from Saclay, so I had to do a reference to Tolkien in my life once. So behind this lyrical talk, what I will try to address is if it's possible to construct smooth bubbling geometries directly from Einstein equation in the spirit of the Microstate Geometry program. Oh, I cannot pass. Yeah. So before going through the outline, let me just motivate a bit what I mean by in the spirit of the Microstate Geometry program. So microstates are geometries are classical fuzzballs that resolve the horizon into non-trivial topologies. There are essentially three main fronts, let's say, three sections where it has been applied. So you have first the BPS and extremal regime of black hole, the non-BPS, non-extremal one, and finally the non-BPS, non-extremal. So the line indicates where we have to go to reach the real-world physics. So most of the effort, of course, have been done in the BPS regime, because in BPS you have nice equations of motions that are linear and nice methodologies that have allowed to construct numerous families of smooth horizonless geometries, which here is a very non-exhaustive list. And from those families, we have been able to dig for new black hole astrophysics from those microstate geometries, like understanding the geometries as black hole microstates, try to explore some ADS-CFT, which has been the subject of Tuesday, and like ADS3, CFT2, ADS2, CFT1, and also maybe to see how information paradox is resolved. Moreover, there is a growing field in this BPS extremal section, which is black hole phenomenology. So it's in quotes because, of course, we are in the fantasy world, but as it has been said on Monday, you can try to extract some kind of universal behavior of microstate geometry that will still remain for the real world physics. Now moving towards on the right-hand side, we can try to construct non-BPS extremal objects. Here it's not numerous family, but only few families. And we can try similarly to do some kind of phenomenology. Now the ultimate goal, of course, as it has been pointed by Nick in the last talk, is to be non-BPS and non-extremal. And here, unfortunately, we are lacking of construction. So in the list, now I should add microstrata, but I mean, it goes too fast for me. But here, so we don't have a lot of solutions, and there are several pathologies. And so drawing black hole phenomenology here is really a question mark. And also the main question, which is like the stability of the geometries. I mean, here we know that microstate geometry are stable due to supersymmetry, but here it's really a question mark. Does the stability of the microstate geometries can go beyond the BPS regime? So the question I will ask is essentially, can we construct relevant bubbling geometries directly from Einstein equations in this right-hand side part? So treating Einstein equation is usually non-trivial. I've done my PhD in Saclay, where the standard law about Einstein equations to build non-trivial topologies with non-trivial gauge field degrees of freedom is essentially you can try, but you shall not pass. It's coupled equations, it's very hard, and then it's better to try to rely on supersymmetric equations and try to break them in a second part. But actually, there are many methods constructed in the past which try to almost linearize Einstein equations. So here I just a small list of it, and what I will focus on is the Vial formalism. So in few words, the Vial formalism is a method to linearize equations for Einstein theories for static axisymmetric backgrounds. So static will necessarily mean no rotation on nothing, and axisymmetry is essentially all sources are on a line. So this is the main goal. We can address now a more precise question: can we develop the Vial formalism in the spirit of the Microstate Geometry program? So in this talk, I will first describe the Vial formalism really from scratch, assuming that even if it's a very old, like it's more than 1 century ago now, I will really describe it from scratch. Then in the second part, I will explain how you can apply the Vial formalism in 6 dimensions, where here you can construct smooth bubbling geometries. Then in the third part, I will study a specific kind of smooth bubbling geometries in 6D, which we call Vilestar, and which characterize as bubble backend. And then at the very end of the talk, I will see how from the Vial formalism we can derive a non-BPS floating brane ansatz in string theory. Okay, so let's start by the Vial formalism. So historically, the Vial formalism have been formulated in 4D vacuum Einstein theory. So the idea behind that is just to assume axis symmetry and staticity, and the metric simplify greatly. You have a time fiber first, without cross terms because it's static, and a 3D base here, rho, z, and phi, which are rho, z, and phi, which are cylindrical coordinates that suit the axis symmetry assumption. And you have two wrap factor, W0 and here, W0 and nu, which are only rho and z dependent because of axis symmetry. So if you input this ansatz into Einstein equation, you get very simple equations of motion, which are linear. So you have a Laplacian of log W0, where the Laplacian is a Laplacian in cylindrical coordinate for a flat 3D base. So even if we have nu here, what W0 will see will only be flat space. And the warp factor nu will be a simple integrable equation where you just have to integrate this and consider log of W0 as a source. So from this, you can derive, from this you can source log W0 by either point particle or rod particles, a rod source, sorry. And the physical solutions are given by rod sources. So a rod is a segment sources on the z-axis. So it's a section of, here I took the size to be mi of the segment at different places of the z-axis. And then the generating function for log W0 is this function there, where gi are some weights for each rod. So I didn't really give the expression of nu because it's not super enlightening, but it's perfectly derivable. So now just have a close look to those functions. So r plus and r minus are the distance to the rod endpoints. So you can see here just basic geometry that the sum here, the sum of this distance is bigger than the side of the rod for sure. And it's strictly equal when you are on the rod. So r plus plus r minus is equal to mi x only on the rod. And here you can see that this guy is vanishing. More precisely, at the rod, you have W0, which go like rho to gi, where rho goes to 0. And E to nu goes to like rho to gi square. So if you fix gi to be 1, you have the time fiber, which is nicely degenerating, like a horizon of a 4-dimensional black hole. And you see also the phi direction here will be finite, like you will have a nice S2. However, in between the rod, so you have W0 will be finite, but E nu will be equal to a constant, which is necessarily smaller than 1. So you have the degeneracy of the phi circle, but because of this di in front, you have what we call a conical excess, in the sense that the periodicity of the local angle here is more than 2 pi. So this manifests itself into a string with negative tensions that we usually call strut. Okay, so just to recap, if you do 4D vacuum Einstein theory, the solutions which are axisymmetric and static are a chain of Schwarzschild black hole given by such a metric where W0 is a product of those generating functions that alternatively shrink at the rod's sources. So I will just explain what this picture means because I will use it very similar ones all along the talk. So here on the left-hand side, I describe the sources on the 3D base, rho, phi, and z. So all the sources are on the z-axis. While here, I describe what the main fiber, like the time fiber or the phi circle, behave on the z-axis. So as I told you, the time fiber is shrinking everywhere I have a rod. Otherwise, it has a finite size, and it's opposite for the phi circle. It's perfectly finite, where I have a rod defining the horizon, an S2 horizon, exactly as this segment. And as I said, I have conical excess here in between each object. So the conical excess, the struts, can be understood in a very nice way, and it has been done by Costa and Pierre in 2000. to try to explain the physics of the interacting black holes here. So of course, if you put black holes, Schwarzschild black holes on a line, they really want to collapse and form a unique black hole. So you need some kind of mechanism to hold them apart. And this is done by those struts. The struts are kind of springs that really push away and compensate for the deficit of repulsion between the two objects. So they are very singular objects. They don't have UV origins. So if we want to construct smooth bubbling geometries, what we need really is to get rid of struts and to get rid, of course, of black hole sources. So this is the main picture. So is there any questions so far about the historical construction? All good. So just before going to the main construction, let's try first to see what happened if I add gauge fields. I mean, what can be the microstate geometry program without gauge fields? So we have to see if we can add gauge field to the problem. So the ansatz is now very similar. I just have redefined a bit the wrap factor. Now it's called Z. And I add one form gauge field, which can be magnetic here. H is a magnetic gauge potential, or electric here, T. So of course, now I have gauge fields. The equations are more complicated. They are coupled in a sense that Z will be induced by the gauge potential. But with IBU, we found a way to still get a linear ansatz, and we can formulate it that way, in the sense that the solution are still given according to one harmonic function, L, which satisfies Laplacian of L equals 0. And everything can be obtained from this L, in the sense that Z is a sinh of L plus a parameter B, which is necessarily positive. And then it's just a matter of integrating those equations. I can obtain H and T, the gauge potentials, rather easily. Still, nu is a bit the same. It's perfectly derivable from L, etc. So now we can play the same game. We put rod source for L with some weights there and derive H and T and Z. And what will end up is exactly the same kind of picture as in vacuum. In a sense, we will have black holes on a line, but the only difference is they can be wrapped by flux. So unfortunately, the flux cannot avoid the fact that the black hole are repulsed by a strut. However, now we have this parameter B, we have a larger phase space, which is nice to explore. So for instance, let's try to see what happens if I take B equal to 0. So if I take B to 0 and I rescale nicely my harmonic function L, I will see that it's Z now, which is harmonic. So Laplacian of Z will be 0, H will be given by this equation, and more importantly, T will be minus 1 over Z, and nu will be equal to 1. So nu equal to 1 means base is flat, and T equal minus 1 over Z is the usual thing we have for BPS solutions, which means that the electric potential is perfectly compensating for the gravitational potential. So more concretely, it means that taking B to 0, we get back to the BPS limit. Here, the solution we will have goes back to a chain of static BMPV black hole we are used to, and the ansatz encompass this BPS limit. In the other side of the phase space, if I send B to infinity, you can see here in these equations, it will kill off all the gauge potential. So sending B to infinity is exactly the same as taking the neutral limit I described in the previous slide. And in between, essentially, you have a chain of Rice and Nordstrom black holes on a line separated by a strut. Okay, so I take some time to explain that, but what is important here is to see that with the Vial formalism, you can easily interpolate from the BPS solutions to non-BPS solutions just by this ansatz and taking B from 0 to a finite value. Okay, so here we want to construct smooth bubbling solutions. So we are very far from that in the sense that I have only described black hole. So how to do that? How to make bubbles? There is an easy trick to do first is to recrotate the solution. If you recrotate time to a circle Y1, so the metric is now Euclidean, and I have a Y1 circle, the black hole transforms to a smooth S2 bubble, in the sense that now my time fiber is becoming a circle, and here the circle which is shrinking, which means that I define an R2 exactly on this segment, and then I have a finite S2 because my S2 has my phi circle has a finite size, and then I have what we call KK bubbles on the line. Each regularity of this R2 here will impose some kind of non-BPS bubble equations that will constrain the internal parameter, which is essentially the rod lengths and how they are separated from each other. So this is an Euclidean solution. So what we want is Lorentzian, so we can add a time direction to it. So if I try to classify Vial solution in 5D, first let's do it in vacuum. So you will have a time fiber, a Y1 fiber, and a 3D base here. So I will have now two warp factor in front of each fiber, W0 and W1, because I have two extra fibers. And I can play the similar game as in 4D. I can source W0 by rod, which will create a black hole, which will induce a black hole on the z-axis, because the time fiber will degenerate, and I will have a black hole, while the Y1 circle will be finite. Or I can I can source W1 by the rod, and then I will get a smooth KK bubble. So in 5D now, I have slightly more diversity in a sense that I can put on a line black holes and KK, smooth KK bubbles.
Yeah, I had a question about the previous slide. So the 4D solution you get by doing the Euclidean transformation.
Yeah.
So after that, so when you do when you go to Euclidean,
yeah.
It's going to be smooth. The 4D base.
Yeah, it's smooth. I mean, if W1 shrink here, essentially you have R2 from Y1 and rho. I mean, you will have d rho square dy Y1 square.
Okay.
So it's a nice R2, and on top of that you have an S2. So essentially it's a bolt kind of geometry.
Mm-hmm. So this is a multi-bolt, multi-bubble geometry, just as a base space.
Yeah.
This is Ricci flat or not?
Yeah.
Oh, okay. Because I mean, one thing which we didn't do was to actually try to build, to build these multi-bolt, multi-bubble things.
Yeah, but here it's pretty bad because you have these struts. I mean,
there's still a strut. There's still a strut.
Exactly. Yeah.
There's still a strut. Okay, this is what I didn't understand.
Do you also, because Y1 has a unique periodicity, do you find that you have to make all the bubbles or bolts the same size? It's a bit like...
It depends. Yeah, I mean, I don't write down the bubble equations. They are complicated, actually. It's a constraint in the size of the bubble. But I mean, it depends of the distance between them.
Okay, but I want to ask, do you have to make them all the same size? Because...
No, the constraint is non-trivial, but I mean, you have here essentially a constraint you did according to RY1, which is like the periodicity of the Y circle, which will need to be equal to some internal degree, I mean, some rod lengths, etc., but they don't need to be the same. I mean, if I take this one to be super far from all the other, it will be a different kind of constraint. But indeed, I mean, there is constraint that will...
Because normally when you pinch off a Euclidean circle, you have to get the periodicity right, and that requires that you make uniquely determines the periodicity in terms of the size of the bolt. And so... Yeah,
I mean, the size of the bolt would be constrained. It's not necessarily all equal, but they would...
But they don't, okay, they don't have to be all equal. That was what I was worrying about.
So if we do the same game in 5D, we have such a picture where now you can alternate smooth bubbles with black holes, but once again, you have struts in between. But it has been observed by Elvang and Horowitz in 2002 that here, because we have different rods, you can glue them without forming one big rod because they are different species. And here, what you will have is essentially the phi circle now is perfectly finite all along the rod configuration, and then you get rid of the strut. So it's pretty impressive because, as I told you, the strut represent the energy you need to repulse the object from each other. And what I'm telling you is when they are very, very close, they are touching, they don't need them. So it has been explained by Elvang and Horowitz by the following reason. A KK bubble doesn't want to be squeezed, doesn't want to be compressed. And so essentially, it will give the necessary repulsion between those two black holes to be pushed away and not collapse. So you can get rid of the struts by just connecting bubbles all together.
The Euclidean base, this is exactly what David and Stefano Kadmadas and Guillaume Bossard did also. I mean, you can take two bubbles and you can just glue the bubbles, but you are basically doing this with black holes also.
Here it's black holes, but then we will see how to.
Yeah, it's very similar. I think it's not exactly the same because we also had angular momentum in our ansatz, whereas this is static.
You're taking two care.
But the basic feature that things simplify when you have them actually coincident, like really touching each other, that seems to be the same kind of physics.
I didn't realize this is what Henriette and Gary Horowitz did. I heard that talk for many, many times, but Henriette was in Santa Barbara and grad students, and I thought, but I didn't realize that this is what they're doing.
Yeah, essentially, it's how to explain how, I mean, this guy can be slightly static in a sense that you remove the spring in between them, and it's still, I mean, the two black holes are not collapsing. Okay.
Pierre, can I ask a quick question here? On the 2 slides ago, I think you had this case where you could get a chain of Rice and Nordstrom black holes plus struts in between them. But as far as I know, we also know that there is this solution which is just a lot of Rice and Nordstroms where the gravitational and the electric force balance, and you have no struts. So how?
Yeah, I think there is.
Okay, fair enough.
Yeah, indeed. I said that you cannot get rid of the strut, but as soon as you take the extremal limit, you're right. I mean, those guys vanish in the sense that nu is equal to 1. And
okay. Yeah. Cool.
Yeah, but I think it's extremal case. I mean, multi-center BPMPV.
Okay.
Okay, so we found a way to get rid of strut, but we still have black holes for sure. So just before continuing to 6D, in the paper last year, we showed that you can indeed also add gauge field degrees of freedom, a magnetic one and an electric one, and you will have exactly the same picture at the air, but the object will be wrapped by flux. So unfortunately, the flux doesn't help for removing struts and everything, but we can still turn them on the same way as I have described it in 4D. Okay, so this leads me to now our main construction in 6 dimensions. So in 6 dimensions, we will add an extra fiber. So as you have seen it in 4 dimensions here, as soon as I add a fiber, I had a new type of rod source. So if I have 2 extra fiber, I will be able to have 2 kind of bubbles that can be sourced on the z-axis and try to play the same game as here. Okay, so let's make it precise. So I take now Einstein theory with a 2-form gauge field, and I will focus on solutions which are asymptotically flat 4D plus a 2 torus. So yes, no.
No, sorry.
Okay. So the ansatz is as follows. So we still have the same kind of ansatz for the 3D base. You have a fiber Y2, a fiber Y1, 2 circles, and a time direction T. So the warp factor are slightly weird in this ansatz, but they make a lot of sense. We have W0, which is the same as before, which will obey the vacuum equations. Laplacian of log W0 is equal to 0. And those Z are the same Z as before. Z1 will couple to the gauge potential H1 and T1, while Z0 will couple to the gauge potential H0. Okay, so now we can apply the same strategy that we have done in 4D. The solution will be given according to 3 harmonic functions, log W0, L0, and L1 for the 1 label and the 0 labels. And I can obtain similarly the Z according to the L, the magnetic gauge potential according to the L by just integrating this equation, and similarly for T. So now what is a generic Vial solution in this framework? As I told you, I can either make the time fiber to shrink, which will lead to a black object, which will be essentially, because the two circles are finite here, it will be a T2 times S2 horizon, so it will be a black brain there. Or I can make the Y1 fiber to shrink on the rod, so it will be just a big, which I call species 1 bubble, where the Y1 circle degenerate, and I will get a species 2 bubble rod, where here it's a Y2 circle that degenerate, but it's still a smooth bubble. Okay, so those are the generic picture we have. So once again, we can try to play a bit with this parameter B. If I send the B to 0, once again, I get the BPS regime. The equation of motion will reduce to the BPS equation of motion. And the generic solution will be chain of extremal black holes plus keep-on-sucking centers. On the other side, I can send the neutral limit by sending BI to infinity. All the gauge field potential will be 0, but I will still get the same kind of topology. It will be vacuum bubbles and uncharged neutral black holes. And in between, taking B finite, I essentially have a chain of non-extremal 3-charged black hole and 2 different kind of species on a line. Once again, everything needs to be separated by struts. Okay, but we have seen that we can get rid of the strut if we connect the bubble all together, the rod, sorry. So here, since we have 2 kind of bubbles, we can connect them. So I will consider solution given by a chain of species 1 bubble with species 2 bubble. So I take 2n plus 1 connected species 1 and species 2 bubble. The configuration look like this. I have those red and green rods on the z-axis. The phi circle will be perfectly finite in between, no stress, nothing, and just the y1 and the y2 circle will alternatively shrink on this axis, defining the axis of rotation. And the configuration is nice and perfectly smooth. So just slightly more details, you can rewrite the 6D metric as follows. It's slightly better to write it that way, where I define these bar quantities and this U1, because the U1 and the U2 are the two quantities that really indicates what happened to the geometry. So those are exactly the same generating functions that I've been dealing with in 4D, which make this to shrink at each odd rods, while U2 shrink at each even rod. So it really indicates where this is equal to 0, this is equal to 0. And you see then when U1 is equal to 0, the Y1 fiber degenerate. The other quantities, Z1 bar, Z0 bar, are just kind of flux decoration on top of it. They are perfectly well defined. They are never 0, and I think always smaller than 1. And H and T also can be expressed easily through our ansatz. So what we get here, sorry, I just forget to say once again, because here I have some R2, origin of R2, it will induce non-trivial bubble equations, non-BPS bubble equations at each rod length. So I will get 2n plus 1 equations that will here, as Nick has suggested before, fix all the rod lengths together. So they will be entirely given according to the asymptotic quantities, essentially the size of the extra dimensional radius. Okay, if I take once again B bigger than 0, I get smooth horizonless chain of two species of bubble in the non-extremal regime and in the non-BPS regime of the black hole. And even slightly more weirdly, I can take a neutral limit where I send B to 0. The full structure will remain intact in a sense that U1 and U2 will be still here. Just all the flux decoration will disappear. But I will still get such a geometry, which is just alternative bubbles on a line. But I have absolutely no gauge field wrapping the geometry. So it means essentially that to produce the geometry, we didn't need any kind of electromagnetic fluxes. Okay, so here we have built our smooth bubbling geometry.
Yeah. Just a quick question. So in that limit, can you say what supports the solution?
Yeah, we'll come back to that. It's exactly the same as what I was suggesting. I mean, it has been done by Egenwagen essentially.
Oh, it's the KK.
Yeah, the KK bubble doesn't want to be compressed. So if you put them on the line, they are slightly squeezed and they really push away.
Thanks.
So yeah, this is a mechanism essentially that held the structure from collapsing. And what else? Yeah.
It's not the flux stabilization you're saying, it's just purely KK monopole.
Yeah, I have to say something. I mean, a KK bubble is unstable. I mean, I want to talk about that later, but it's unstable. So essentially it wants to grow in size. So that's why the full structure is not collapsing, in the sense that the bubble in the middle wants to expand, and then it will make the structure not to collapse. So the structure doesn't collapse just because of this expansion of the bubble, but the flux will be necessary to prevent from expanding. So the flux are not here to prevent from collapsing, but more from expanding. This is something we discuss in our paper today. But here, indeed, I mean, if I take the neutral limit, I still have a geometry which is not collapsing, in the sense that the bubble are just pushing each of the neighbors away. But it's very likely, like in the neutral limit, the big structure expand like the vacuum instability of the vacuum KK bubble. So the flux are here more to stabilize the geometry, but we can still take a neutral limit, even if it would be surely unstable. No question anymore? Okay, so we can derive the profile of the solution in 4 dimensions by compactifying along Y1 and Y2. You will get massive solutions due to this warp factor in front of time, and it will be singular at the rods. You have 3 gauge field after the compactification, so you have 3 charge, 2 magnetic and 1 electric. So what we found are smooth geometries without horizon, and which has the same constant charge as a 3-charge static non-extremal black hole. So here I describe mostly the geometry very close to the rods, etc. The question is now, how do they look like? So this leads us to the third part of the talk, which is the description of Vilestar. So the Vilestar, it's a nickname we give to a very specific type of geometry obtained from the smooth bubbling geometry we construct. It's essentially just taking the number of bubbles in a chain to be very large. Okay, so it's exactly the same configuration, but I just doesn't take 2, but a huge number of bubbles. So the first thing to do before trying to study how the Vilestar look like, it will be to fix the bubble equations. So the bubble equations I didn't write down, but they are pretty complicated. But you can try to find kind of approximations to see how to satisfy them. And what we found is that all the rod lengths, mi, are fixed according to the extra-dimensional radii, ry1 and ry2, such that you have an extra factor n power minus 3/4. So n, I just remind, it's a number of bubbles. So if I take n to be large, the rod lengths here are even more than microscopic. It has been highly squeezed in the chain, but they are mostly the same size all along the chain. So the bubble in between are very, very small, but because we have n of them, if you multiply by n, you see that all the macroscopic quantity for the Vilestar will scale like n power 1/4 ry1 or ry2. And then the 4D mass, the charge of our Vilestar will be way greater than the ry, way greater than the radii of the extra dimension. So you can construct with such a methodology a big macroscopic object. Okay, so this is how to fix the regularity condition. Now let's go forward and try to describe what is the geometry of the Vilestar. So for this, it's slightly better to take not cylindrical coordinate rho z, but spherical coordinate, which are slightly more centered on the surface of the star. So 2m here is the full side of the rod configuration from this point to this point. And we take then the r theta coordinates by such a change of variable. You can see that r is necessarily bigger than 2m to have a rho which is necessarily positive. And if you take r equal to 2m, rho equal to 0, and z goes from minus m to plus m. So r equal to 2m really describe what's happening here at the surface of the star. So, okay, I will try to describe how the geometry look like. So I will start by describing the surface of the star. So at r equal to 2m, as I said earlier, you have a big fat S2 here, which is finite and big, and the axis of rotational symmetry is alternatively played by those extra circle, y1 and y2. Moreover, as I said, I mean, you can wrap the S2 and the T2 also by flux, but they can be easily turned off without making the structure to collapse. So the full structure is not held by electromagnetic flux, like in the BPS story of microstate geometry, but it's held here by pure topology. Moreover, I mean, because the system as a configuration is highly axisymmetric, you can expect this S2 to be very, very much squashed. Actually, what we can show is computing the physical distance in 6D from the North Pole to the South Pole by just moving around along theta, or from the east to the west on the equatorial plane. You will see that the distance is equal to the mass of the guy square over the extra-dimensional radii, or from east to west is only the mass. So essentially, if you do the ratio of this distance over this distance, it's scaled like the mass over the radii, so it's very big. So it will take a lot of time to go from those 2 points, while these 2 points are way closer. So it's mostly a concombre geometry. So I try to describe a bit how it looks like at r equal to 2m. The Vilestar is a large squashed concombre, which is spread by this axisymmetric bubble, where here in this place the red circle are shrinking. Here it's a green circle, and then you have this kind of S2 spread by small bubbles, axisymmetric bubbles. So here it's kind of picture you can imagine for the surface of the Vilestar. Okay, let's now try to describe the geometry of the Vilestar at away from the surface. So at r bigger than 2m, I mean, you have seen the metric. It's very hard to understand what's going on because of those big products. I mean, it's almost unreadable to see how the geometry look like. But hopefully, when r is bigger than 2m, you can apply this mathematical trick, which is called the Riemann Sum Approximation, which essentially simplify some big sum or big product to an integral form, and you can integrate and massage it a bit and get a simpler version. So what we find, for instance, for the wrap factors that we call U1, which is this big product, by applying Riemann sum approximation, you will find that it's essentially equal to square root of 1 minus 2m over r, for r slightly away from the surface. You see, it's 2m times n power minus 1/2, where n is taken to be large. So just when you're slightly away from r equal to 2m, it will be perfectly indistinguishable. The wrap factor will be perfectly indistinguishable then compared to this value. So applying this kind of technology to each wrap factor in the metric, what you will find is the neutral Vilestar, so when all the gauge field degrees of freedom have been turned off, is indistinguishable from such a background. So here I just change a bit the order. Here it's n power minus 1/2, but you can show that it's essentially 2m, so the surface of the star, plus the small bubble size, which is very small. And so what you can see, so this is the metric you get, the approximated version of the Vilestar away from the surface. What is quite incredible is when you apply an approximation to a background that solve Einstein equation, of course, you do not expect the approximated solutions to solve Einstein equations because it's nonlinear equations, so everything gets messed up. But here, it's kind of strange conspiracy, but this solution, which is the approximated version of the Vilestar away from the surface, solve Einstein equation on their own for any r. The thing, it has a naked singularity at r equal to 2m. As you can see, you have this kind of weird degeneracy of the T2, and also this factor 1/4, which is slightly weird, which make the theta fiber to blow up. So we will come back to how this metric look like at r equal to 2m. But it's quite surprising that our Vilestar is really indistinguishable from this solution of Einstein equation. Then, okay, it's just, I will not really detail how it look like, but if you turn on the flux, you get a more complicated version of the metric. But the basic ingredient is that you have some warp factor due to the fluxes on top of this geometry. Here you can see that it's a magnetic monopole kind of source. And similarly, I mean, you can get a two-form gauge field. So here is what the Vilestar look like if you turn on the fluxes. Okay, so now let's try to describe then how the Vilestar look like away from the surface, which is essentially given by this metric. So as I told you, I have a naked singularity r equal to 2m. And moreover, the bubble size scale gets smaller when I increase the mass m. So when I increase the 4D mass of the object, so I increase the number of bubbles, the bubble size will decrease. There will be smaller and smaller, those microscopic bubble. So it means that the Vilestar will scale more towards this singular solution and will resolve it into these non-trivial topologies I have described by studying the solution at r equal to 2m. So it's a first example of such a resolution in a very non-trivial, non-BPS, non-extremal regime without any BPS supersymmetry assumption and just treating Einstein equations. So now let's deal a bit with the singularity at r equal to 2m. So if you have a close look at r equal to 2m, this factor blows up. So the theta fiber blows up. What does that mean? Essentially, it means that the S2, described by theta and phi, will at one point opens up and blows. So here I just represent the area of the S2 as a function of r over 2m. So here is when r is quite large, you have the usual r squared growth of the area. And here it's just looking very close to the singular point r, very close to 2m. So the black dots are the area of the S2 of this singular metric, while the red dots is the red line is the value for the Vilestar in particular. So you can see that they match very, very well. The Vilestar mimic perfectly, as this approximating metric mimic perfectly the Vilestar until r very close to 2m, and then just avoid the singularity and ends up as a smooth locus at r equal to 2m, which have been described before. But what is important to notice here is that because it suddenly opens up, it means that you get a minimal S2 slightly away from the surface. So you have a kind of geometry which reminds us directly here a bubble backend. I hope now you understand a bit the picture. So we have a geometry where the S2 is just as soon as you get close, decreasing, like the usual spherical behavior. And then at one point, if you cross a certain circle, it just blows up into a new space, just full of bubbles everywhere. So it just opened up there and you have a bag full of bubbles, which is perfectly smooth and nice and caps off the space-time smoothly. So this is now the picture I can depict for the object we have constructed. We have identical features when the flux are turned on. As I told you, it's just kind of a decoration on top of this geometry, but you will have the same kind of hole. So you can imagine that from far, you will have a hole where it's open up into a very big space. Okay, so now, I mean, I'm working in the Microstate Geometry program. I want to see how the Vilestar then compare to a black hole. So I take a black hole with the same charges, so 3 charge black brane, static, and I want to see how this Vilestar geometry is comparable to the black brane of the same charges. So a relevant quantity to compare is the minimal S2 once again. I have a minimal S2 for the Vilestar, which will give me what I see from far. And I have a minimal S2 for the black hole, which is obviously the area of the horizon. And the question is this very much compact, more compact, scaling with the area of the horizon of the black hole with the same charges? So what we find by just looking at all regime of charges and masses is that the minimum ratio you can get is 1.5, in the sense that the Vilestar is 1.5 bigger than the black hole of the same mass. So it's not scaling towards a black hole, but it's still very much ultra compact object. And here I just show some for different values of mass and charges. You see that essentially the ratio which describe the compactness of the object is between 1.5 and 2.3. So all Vilestar are very compact objects, but they are not really scaling towards the black hole. So what will be interesting to push forward is how do they look like if they are in the sky. Essentially, you will have a minimal S2 surface where light can get trapped. You have a very big space inside where light can move around and comes out. It would be interesting to push forward by to see if geodesics get trapped for a very long time, how the multiples of the object behave. So these are things we want to do in the future. And then just for the 2 minutes remaining, let me try to see how the construction we have done in 6D here can be extrapolated to a more top-down approach. So I have used 6D theory with a two-form gauge field. So it looks like a bottom-up approach, but actually, I mean, I always kept in mind that we can do actually a top-down construction. There is a question or something? No.
I'll wait for the end.
Okay. So I can embed our solutions in type 2B very easily, but it's just adding a T4 metric on top of it, and I get a 10D solutions. All the type 2B fields are trivial, except this two-form gauge field, which are the same as I gave. And then you can describe our system as simple KKM D1 D5 solutions. So the equation of motion we have derived are linear D1 D5 KKM equations in the non-BPS regime and also in the non-extremal regime of black hole. So the generic solution will be chain of non-extremal 3-charge black holes D1 D5 KKM, or those smooth species 1, species 2 bubble, which will be simply D1 D5 KKM bubbles and KKM bubbles. So we have seen that to prevent the full structure from collapse is either those artificial struts, which are singularity, or either connecting bubbles, which remove the struts away. And the Vilestar then in this picture are smooth chain of D1 D5 KKM and KKM bubbles, which is in the same regime as D1 D5 KKM black holes, as a Svetitanium 3-charge black hole. And we can play with the flux to turn them off, where the black hole would be simply an embedding of Schwarzschild and the bubbles will be vacuum bubbles. Okay, so can we go further and try to derive directly from string theory a nice non-floating brane, non-BPS floating brane ansatz? So this is perfectly doable. Actually, I have shown, and we hope to publish a paper very soon, that if you take M2, M2, M2 KKM system, assume as Weil did in 4D axis symmetry and staticity, everything can be written down in a very simple way. So you have the 4D base where we are used to, where here it's the three-dimensional part, and here you have a fiber with the swap factor Z0 and Z0 here. It can remind you the BPS ansatz. You have 3 T2s, which can be wrapped by M2s here. And then you can apply the similar kind of techniques that we've done before, in a sense, Zeus TI, T1 and Z1 will be coupled to each other. The H0 and Z0 will be coupled to each other, and those lambda there are something which are not there if you take the BPS equations of motion, but here they are here because it's directly Einstein equations. So if you apply the Vial strategy we have detailed before, all the solutions are given by 8 harmonic functions, 4 which are these W's, and 4 which has the L corresponding to the gauge field pair T, Z, or H0, Z0. And everything is simple to write down. Once again, you have the BPS limit by sending the B to 0, and you retrieve the M2, M2 KKM BPS ansatz. But for generic B, you move along and you move in the non-BPS regime of the solutions. And the generic solution will be 4 charge Fetich nu, black hole, static, plus several kind of smooth bubble, which we can construct easily, as I have done it for the Vilestar. And even you can take at the very end of the phase space for those Bs, you can take the neutral limit where everything, all the gauge field are turned off, but you still get these non-trivial topologies. So there is a super large phase space to explore, for which our Vilestar are just a subclass, and which we'll hope to do in the future. So, okay, let me just conclude now. So I hope I have convinced you that we can construct non-trivial topologies a la microstate geometries, just treating Einstein equations and without any supersymmetric assumption. I have described Vilestar, which has interesting objects obtained from those ansatz. So they are not really scaling towards a black hole, but they are very nice geometry where they have a minimal S2, which opens up in a very big bag of bubbles. So we can wonder if it's a generic features of microstates, if we succeed to turn on more degrees of freedom to decrease this minimal S2 size towards this S2 of the black brane, and then scale it very closely, and then just the space will open up in a very big bag full of non-trivial topologies. So this is a kind of feature we can imagine for a microstate geometry in the non-BPS regime, which is not visible if you deal with BPS solutions. Then I have shown in the very last part and very quickly that the Vial formalism allow to derive a non-BPS floating brane ansatz for M2 KKM system, where there is a very big phase space, which will be good to explore. Then, just for the outlooks, what would be nice is to try to do some phenomenology of the Vilestar and try to compare them with black holes to send lights in it. I mean, since it's a very big bag, what the light does in this background are really interesting. Compute the multiple moments, try to solve also the scalar wave equations, something we can imagine. Then I didn't really discuss this question, but there is a huge issue of stability. So in the paper of today, we try to discuss that. I mean, vacuum KK bubble are unstable and grow in size, but it has been computed that if you had the right amount of fluxes, they are stabilized. So we hope that our Vilestar with slightly a bit of flux are stable object. Then what will be great is add rotation in a similar manner that David, Guillaume, and Stefanos did. In a sense, you take kind of like touching care solutions and try to make them bubbling in a nice way. This would be great to add those kind of rotation degrees of freedom in the game. Then just for the floating brane ansatz, the BPS one, which has been derived by Yosif and Nick 15 years ago, was also adding M5, M5, M5P charges in the in the BPS regime, which were really important to construct smooth geometries because it allowed Chern-Simons interaction. So here the question is, can we do the same, add two charges and still get a linear equation in the non-BPS regime? This is also something I have in mind. So I will stop there, and I thank you for your attention.
Thank you very much, Pierre. Very nice talk.
Thank you.
So questions. Nick's had his hand up for a while, so he gets first pass.
Just quick issue. First of all, I just want to understand, you get this sort of apparent naked singularity when you step away from it. So from a four-dimensional perspective, what does this thing look like? Is it above extremal, or is it, you know, if I step away from outside RS2M and I'm just live in 4 dimensions, what does it really look like if I'm a four-dimensional person?
So at the rod, essentially, like this guy.
No, I understand, you know, RS 2.5M.
Well, then it's
is it extremal or?
So it looks like you have a minimal S2. It's like a black hole. You have a minimal S2.
Yeah,
so
but okay, but I'm in 4 dimensions. Black holes have mass, charge, and angular momentum. So what's it got?
Yeah, but the light, I mean, you will see what the light explore inside. So you will see this minimal S2. Indeed, I mean, the S2.
Okay, but I'm in 4 dimensions. I just want to know the quantum numbers from the 4-dimensional perspective.
I mean, from the 4-dimension perspective, the S2 is shrinking.
Yep, good.
Okay.
There's a mass. How many
mass? Okay.
Then you have charges, right? Would you?
Yeah, it has 3 charges.
Let me ask my question. I'm at 2.5M. I don't see any of this detail. I don't see any of these bubbles and so forth. I just see an object in 4 dimensions, 3 + 1 dimensions. It's got a mass. That I've got.
Yeah,
it,
mass.
It has a charge, but no angular momentum.
Exactly. It has 3 charges that you can tune.
Does it look extremal or non-extremal?
It's in the non-extremal regime of black hole.
But yet it looks like it's got a naked singularity. So that's sort of puzzling to me.
No, it doesn't have a naked singularity.
No, I know it looks like it does. I didn't say it has one. It looks.
I mean,
like
the light. I mean, what you will see from the object is the light that come in and will explore this 6D dimension, this dimensional framework.
So I've got another related question to that. I'm trying to think about it from the 4-dimensional perspective. Can you go to the slide where you showed the bag and the torus and there? Yes. Okay. So the bag does that involve the 2 torus or not? Or is it just the 2 sphere and the radial coordinate?
The bag is only the S2, essentially.
Okay, so let me ask the question in another slightly different way. Suppose I compactified this on a 2 torus. I just did the standard reduction to 4 dimensions. Then it looks like I've got a set of geodesics that go in on the sphere, so they're converging as they shine in. So I've got a shell of light going in. They go down your throat, and then they get to the bag, and then they expand from the 3 + 1 dimensional perspective. Now, I understand that you might have got some.
This is not allowed to exist in 4 dimensions, right?
Well, exactly. I was about to say the Ray-Choudhury equation forbids that if the energy momentum tensor is everywhere positive. So something clever or sneaky or so on is happening that enables these things to diverge.
Nick.
Yeah.
So if you go down to 4D, there's a non-trivial scalar profile.
Good. Now we're getting
and this is where the magic is happening. And this is so this scalar is effectively producing a negative energy density from the perspective of 4 dimensions. Thank you. You've answered my question. It doesn't happen though until you come right on the back.
No, I'm happy you've answered my question perfectly. That's what I was trying to get at. There's something from the 4-dimensional perspective that's violating all the rules of 4-dimensional black holes.
Yeah, it's the same thing that happens with Witten's bubbles, right?
No, I'm happy. You've answered my question. I've suddenly understood what you're getting at, and I've got it. I'm happy.
By the way, as a side comment, I cannot raise my hands because I'm a host. As a side comment, there's like this Busso principle. So Busso had some arguments that, essentially when you have some surface, there's an entropy inside, which, can only increase. And, it's similar to what Nick was arguing. So I think this provides some counterexample to that. Or if not, maybe there's a generalized Busso principle, but you guys should look into these Busso papers. Maybe your construction just invalidates all these conjectures which he did.
Maybe vacuum, no?
I mean, so our construction sort of avoids quite a bit of the standard, no-go theorems and that you have in 4D. Precisely, from a face of it in 4D, all of those conditions are satisfied, right? You from 4D you get something that is singular, something that is consistent with all of the 4D stuff. But the way that you avoid it is actually when you come very close, you have a high dimensional structure.
Yes, but the shrinking of the sphere is just a 4D phenomenon.
Yeah, so but my point is that phenomenon you cannot experience in 4 dimensions.
Yeah. What's happening, Joseph, let me try and explain. Tell me if I'm right, Ibu. So basically, when you compactify down to 4 dimensions, it's not just gravity. You've got a scalar.
Yeah.
The scalar is the size of the torus, presumably. And
Yeah.
so that scalar from a 4-dimensional perspective is, even though it's perfectly kosher in 6 dimensions, from a 4-dimensional perspective, it's providing a negative energy density, which is allowing the geodesics to diverge.
No, I would phrase it this way. In 4 dimensions, what you get is a theory of Einstein's theory of scalars. And indeed, if you have such a thing, most generally they just want to be very singular, right?
Indeed.
And that picture is consistent with all of the 4D theorems. So that is quite nice. So all of the 4D theorems that you might dream of or want to impose for GR are there. But there's the loophole that is here is that actually those 4D are not just some random scalar, they're scalars that describe some torus. Right?
But are you or not violating the energy conditions near the bubble, near the bag?
So the very notion of coming at the bag that doesn't exist in 4 dimensions. Because in 4D you just see a singular beast.
I see.
The 4D metric is just a singular beast.
But the singularity is behind the bag, so you first go the bag and then you hit the singularity, right?
That's right. But the point is that before you would sort of so if you're an infalling guy, before you would hit what is the 4D singularity that is consistent with all 4D theorems, is that this thing opens up to some high dimensional object, and then you experience the high dimensional physics.
Let me try a parallel, Joseph. When we did our first microstate geometries, you used 5 dimensions and just a circle to do some magic that made the 4-dimensional solutions that look singular, multi-centered things into perfectly smooth bubbles. Exactly. Here they've got a magic that involves a torus and a scalar, which is the volume of the torus. It's the same sort of magical principle, but it's richer and different.
I think it's
different. The point is that you can avoid 4D theorems. There's an important loophole to all of these 4D theorems. That is, you can satisfy all the 4D theorems and have something that is smooth in higher dimensions. And that is a point which I think people do not appreciate quite well. Right? You can say all the things you want to do in 4 dimensions, but there is always an important loophole that as soon as you change the dimensionality of your object at some point, right, everything that looks singular and pathological all of a sudden are just capturing the fact that you have a high degree of additional degrees of freedom that are becoming light and important in that case.
But I think this Boussole principle is actually a 10D. It can be done in any quantum theory of gravity. So his principle is that you have some surface, and the surface cannot shrink. So if you're in 10 dimensions, you can, or in 6 dimensions, you can just compute the surface of this bag.
Again, it's gonna depend on what the assumptions of theorems are.
But like with all these theorems, I think it would be a public service. It'd be a public service to actually see how it gets around the assumptions of Boussole's theorem.
I think it would be very nice to understand how this is violated. It would violate this Boussole principle, and maybe it's just. I mean, I think it's very important to go to the bottom of it.
This is the danger of physicists quoting mathematical theorems. They usually forget some of the stipulations of the mathematical theorems, and so we drove microstate geometries through all of those theorems because there were assumptions that we always tended to forget. And so Boussole's theorem's probably got some perfectly reasonable assumptions that this is violent, this is getting around. But it would be really nice to have that out in the open.
Topology, actually, I think it's topology. But anyway. It's very nice. It's really cool. I mean,
it's pretty nice. I mean,
so can I think I got these discussions got a bit more confused because I thought I understood and I don't. Can you go to that plot where you show the minimal area surface? Yeah, there you go. So is this a 4D solution to Einstein equations plus a scalar field?
No, here's a S2 is in 6D. I mean, it's really like this metric. I'm plotting the S2 of this metric. Phi and theta are there.
Is that really 6D. This is a 6D? Okay, so these plots that you're showing there, there is an orange curve and a dotted curve. They are just they are both for 6D, or is one of them 4D and one?
No. The black curve is the area of the S2 for this metric That's why it's diverging here, because you have this kind of factor.
Yeah.
And the red is a real solution I get from the Vial formalism. This is an approximation of our
Okay, but they are both 6D dimensional.
Yeah, but both are 6D. I mean, in 4D, I mean, you have bad scalar here, so you cannot really study the thing really close to R equal to 2m in 4.
I mean, in 4D, everything looks good and well behaved all the way through the mouth of this thing, which is where
okay.
And in 4D, if you're very far away, I mean, if you like, you don't even have to be super far. Just be, you know, a tad bit away from the mouth of this thing. What you see is just going to be a solution with a non-trivial scalar profile and some charges when they're turned on. So and in fact, there are many, you know, sort of papers out there that analyzes 4D scalar backgrounds and try to come up with sort of what people call modified gravity, and many of those things interesting exist. And in fact, if you look at those papers, the dynamics of geodesics and the dynamics of many things can change quite a bit just due to the presence of the scalars. And we actually observe some of these things in the paper. And there are actual physical large-scale manifestation of having scalars that you could see up in the sky.
No, I think that's very interesting. Now, one question is, one may argue this is a very atypical microstate. Would you say that's the case?
So I'm not sure I can call it a microstate or not a microstate, because if you say a microstate, it refers to a specific black hole, and then you have the microstate geometry, right? So here we're not even that ambitious.
Yeah, I mean,
what we want to do is just like, can I build, what are the mechanisms that I can use to build smooth things before I can even try to give them interpretation or whatnot? Okay. And I think I'm fairly conservative from this point of view. And even from this point of view, this is very interesting just for looking up in the sky. What can you build that can look like black holes when you come arbitrarily close to it? Right.
Yeah, I mean, it's not really scaling towards the black hole. I mean, to be a microstate, you need to also construct them in the near horizon region. Here you cannot, because I mean the S2 we have it doesn't scale toward the horizon. So we need
as a Schwarzschild microstate, you don't. I mean, it's not as a microstate for a black hole with a big ADS3 throat, but for a Schwarzschild microstate, this is as good as any. I mean, it's probably very atypical because it's very big.
Yeah.
But I wouldn't. I still don't think I should use those terms yet, because I can't precisely compare them.
For me, there is no. I mean, it's too far ahead to say that it's a microstate.
You guys can charge it up, right? You can give it some charges, right?
Yeah,
So these things have charges.
ADS3, for example.
Yeah, but I mean, it's something we study. I mean, you cannot take the near. I mean, at least I didn't try, but I think it will be very hard to make it asymptotically the near horizon geometry of a black hole.
No, but just put it in ADS3. I think that's enough.
I think it's hard. I mean, ADS3 also it will be extremal kind of thing. So
I guess more generally, the question is, can you get a near extremal regime or near BPS regime?
Yeah, those exist. I mean, those exist. We can. So in some of the transparency, we are sure that you can dial the charges and make it look extremal.
No, to being
actually the standard extremal sort of structure that you know.
Okay, so then there should be an ADS throat of either 2 or 3, ADS2 or ADS3.
That's right.
No. I think I mean, I don't know. It remains to be said, but I mean, if you take release a parameter where you get BPS, the BPS solution, of course, I mean, you get back to the BPS equations of motion. So the solution we construct will be the BPS one. But if you get slightly away, it's hard to know how I mean, if you can make the asymptotics to be the near horizon geometry.
What I mean, did you look at it in detail? Like what didn't look? Oh, okay. Yeah. No, because that will be interesting, because on generic grounds, if you can take a near BPS limit, you should be able to get an ADS for some a finite length ADS2 or ADS3, depending on your dimension.
This is possible, but
for me, because the minimal S2 size cannot scale toward the side of the area, I think it's compromising a bit the construction. You cannot zoom in to the horizon but because our guy is bigger, I mean, you cannot construct there.
Okay, so you don't have a parameter that would control the length of this
Exactly.
ADS between the top of the ADS
Yeah,
and the bag.
I think it will be hard. So I think we are lacking a bit of ingredients. But what is nice is it gives a kind of picture. I mean, if you succeed to turn on more degrees of freedom in this construction to make this ratio to be closer and closer to 1, and even to have a parameter to make it exactly to 1, is kind of vision where the microstate will be a kind of minimal S2, which is really close to the S2 of the horizon, where it's just open up like a bag.
Yeah, as Pierre is saying, the structure so far is very rigid. There's no moduli parameter.
Yeah.
It's I mean, the bubble equations and the number of free parameters are equal and independent. So you actually, there's no free, the only free parameters are the charges that you can dial.
Yes, is B.
But the charges, what they do, they just give you some overall sort of structure. And as Pierre explained, and what having these charges do is that bubbles themselves, they want to expand. So the structure is self-supporting, but the outer bubbles, they want to just blow up and explode. So having the charge is the thing that sort of holds together the outer structure, while the inner structure, you know, they fight among themselves and just sit there, and that's very, very rigid. And that's very rigid, and that determines basically how you move away. It determines the size of the bag, where the minimal surface is going to be. But this is a very interesting question. What can you do to actually turn on some moduli and additional parameters, or even whether you can expect for that to even exist, right? That's a very interesting question. One, I don't think we have the best ideas yet, but that is something to do. The exciting thing is that you can sort of push this all the way up to M theory and type 2B, and actually fits with all of the sort of standard floating brain ansatz that Pierre described, which means that there's another window to connect further in string theory and in string tree setup. So that is one end of the story. But from the sort of more down to earth story, you know, the question that Nayesh might be interested in is the question we want to ask is, what else can you build that is interesting, that becomes completely smoothed out in higher dimensions, that mimics a black hole, looks like a black hole, is as compact as possible, that can show up in the sky and actually could look different at macroscopic scale? And this is an example of one of those things.
Yeah. Very nice, very nice. So do we have one final quick question or comment from anybody before we close the YouTube part? And we can have a few more minutes of informal discussion if not.
I really think it's worth pushing on this sphere, which becomes smaller and larger again. I think this is really going to break a lot of eggs. So, you know, you guys, I encourage you to enthusiastically to figure this out.
Okay,
we have our own agendas also.
It's really nice, really cool.
Thank you.
Second that, absolutely. We should probably take a pause. So I think
good, yes.
Yeah.
So
thanks again.